Any questions first? Nothing? You all did the homework? All right, no problems? Okay. So we've covered plane wave propagation. We derived it from Maxwell's equations. Covered the intrinsic impedance. We covered alpha and beta, or gamma. And we covered phase velocity, omega over beta. We talked about two conductors. Now we're going to talk about insulators, really dielectrics, but lossy dielectrics. And I want to make sure this is a little tricky. You don't have textbooks? Does anybody have a textbook here? Oh, I see. If you look at the section, dielectrics is before conductors, but they're called lossy dielectrics. Now I've got to make sure you understand something. Whenever we're talking about current flow in, really, I should say current density and either conduction or displacement current related to propagating waves, you have to understand something. Curl of H is actually technically equal to J plus the partial of D with respect to D. That's Maxwell's equations. There are no assumptions in this one. It's just stated explicitly. Now, when we go to the phasor domain, we assume everything varies as e to the j omega t, and we take the real part of e to the j omega t times the phasor form of, say, e, and take the real part of that to get the actual time domain form. Do you all remember that? If we stay in the phasor domain, this equation becomes sigma e, and typically there's a phasor tilde, but here's how you always know you're in the phasor domain. If you see a j omega, that can only mean you're in the phasor domain, or something at an angle, I mean a magnitude at an angle, a complex number. Then you're going to get plus j omega epsilon here times e vector phasor. And here I replace d with epsilon e, and I replace j with sigma e. You all remember this, class? Now when you do this, this is related to real current flow. And this is related to displacement, I should say real current density flow, but real current flow. This is displacement current. Current density, really. All right, now, why am I going through this? When I try to explain the difference. If you talk about real current flow J, and you had a bar like this, and this is the best example I can give. It's not actual, but it'll help you. Do you remember me talking about this earlier, class?
Like last class?
Yeah.
Yeah.
All right. Now, if you could somehow get a spray gun and you had a blue paint, and you take a look at positive charge, actually the electrons, really. But if you could assume the charge was moving and you would watch it, real charge would continue to circulate around there if it was positive charge, or negative if it's electrons, it's going the other way. You with me, class? The charge is not bound to any region it moves. When you talk about displacement current or displacement current density, think of a capacitor. If you have a capacitor here, and you put plus or minus a voltage here, if it was a DC voltage, nothing technically would flow between the plates. You all with me on this, class? But you would accumulate a charge, and there would be a loss of a charge there. And then, if this voltage was time varying, you would have a plus or minus charge buildup on the plates, and you would actually get current flow through that capacitor, but the current flow through the capacitor, I in the capacitor would be C times dV dt. Now, do you all remember this? The only time you can have flow in a capacitor is with a time-varying voltage. Does everybody follow me on this? If it's an ideal capacitor, how many know that?
Time-varying voltage, like a sinusoidal.
Yeah, but I mean, what is it in the phasor domain? It's what? The I would be the voltage divided by, think about this. What's capacitive reactance? It's 1 over j omega c, right?
Yeah.
So if I wanted I in a capacitor at a constant frequency, it would be V in that capacitor in the phasor domain divided by 1 over j omega c, or it would be j omega c times V. With me? Now if the frequency is 0, if omega is 0, no current. But that's the way we talk about displacement current density. It has to do with actually charge being displaced at the plates, or some way, shape, or form, there's a accumulation displacement of charge, typically. I gotta explain something now with this term. In free space, epsilon is epsilon naught, but there still is a displacement current density we talk about. No real charge is moving, but it has the same units and the same effect as this, as real charge flow. Is this making sense to you? Now, in real materials, dielectric materials, and I'll put it here, you're going to have bound charge. This part I want to make sure it's real clear. So when you have dielectric materials, you don't have charge that's free to move, but you have charge, you might say, it looks like a plus charge and a minus charge, and there's something like a spring holding them apart. And there would be not just one, but a whole bunch of these. These simply represent, that's a spring there, not a resistor. What it represents is what's going on inside a dielectric like mica or any kind of a dielectric material. Dielectric materials typically are considered insulators, though they don't allow DC current to flow, at least not much, almost none. Follow? Now, if you apply an electric field, think about it. If I apply an electric field in this direction, then these molecules stretch. This molecule and this molecule will stretch. And as they stretch, there's movement of charge. Y'all follow me? As a matter of fact, if it was a time-varying field, there'd be a time-varying electric field there, time-varying force on this, and these little molecules would move back and forth. That's causing a current flow. Y'all follow me? A current density. But they're bound. They can't move outside of that region. They're bound. And they only, when the frequency goes to 0, there is no current flow. The energy is stored in the actual electrostatic retraction and repulsion in the molecules. Now that gives rise to two types of, when we talk about dielectric at a constant frequency, we talk about the real component and the imaginary component. This is important. So I'm going to come over here and talk about it in a little more detail. But I want to make sure you have kind of in your mind, you have at least you imagine what's going on. So when we talk about, let's assume the conduction current density is 0. So that means that sigma E is 0. And if E isn't 0, it implies that sigma is 0. So there's no real conductivity in the sense that anything can flow, all right, from the battery to, or it can't flow through the thing. You with me? It's bound. What we do is we say that if that's the case, the curl of H can be rendered, and you'll see why, as, since J is 0, I'm going to leave it alone, as J omega, but instead of putting epsilon, they call it epsilon complex. I'm going to put a hat here times E. Now that's similar to epsilon, but I want you to watch this. And I'll give you the page number in a second. So epsilon complex is equal to epsilon relative times epsilon naught. And it's going to be minus J here times epsilon double prime. You're going to have to just go with me on this one. This is usually represented as epsilon prime. So epsilon complex is epsilon prime minus J epsilon double prime. This is the complex permittivity. And by the way, in the book, you got a PDF of it. Take a look at the region on dielectrics. There's going to be an equation for complex permittivity. Can you give me that number?
Yeah. 6.44.
Okay. Now, how does this actually work? I want you to watch over here and you'll see it. Remember, complex permittivity is epsilon prime is epsilon relative, epsilon naught. It's just like the normal epsilon. But then there's this minus j epsilon double prime. And this accounts for the actual bound charge motion where you have a loss. Just keep watching, you'll see it. So this becomes, curl of H becomes j omega epsilon prime minus j epsilon double prime times E. Everybody with me on that? I'm assuming sigma 0 and I'm putting in what we define as the definition of complex permittivity. You'll see why they do it in a second. With me? All right, now keep going on this. I have curl of H. Now, I'm going to rearrange this, but J times J is what?
1, -1.
J times J is -1. With a minus sign is +1. So we get epsilon double prime, or really I'll put omega epsilon double prime. And then we're going to get plus j omega epsilon prime E right here. I should say E's in both of these, pardon me. E would be here. And it's going to be plus j omega epsilon prime times E here. And they are vector phasors. Are you with me, class? Can you all see this? Now listen up, this is important. Let's go back to the original curl of H equation. Remember when curl of H was equal to sigma E plus j omega epsilon E? Remember that? That was the one where we assumed there was conduction current or there was no other type of current other than displacement current, which is j omega epsilon times E. With me? You see how this is strict real? And this accounts for the loss, right? The sigma E accounts for loss. With me on this, class? You see this? This is strict real. So you can think of omega epsilon double prime as sigma, but it's not sigma. It has the same exact effect, but the charges related to that formulation are bound. They can't flow through the lattice. You with me on that, class? And also, you'll notice one thing. This loss, omega epsilon prime, it's just like sigma. It's a function of frequency. As the frequency goes to 0, it becomes 0. Can you all see this? Now, do you remember what the, when we talked about did you remember power density and electrostatic energy density in EMAG 1? All right, so think about it. What was the electrostatic energy density? Well, let me do it this way. When we talk, no, I'll do power density. What was power density? Power density, well, just think about it. Power density. What is power always? And we're electrical engineers. Amps times volts, right? But it's a density, so amps times volts. If it's a density, power flows, right? So it has to go through an area. An area has units of meters squared. With me, class? Do you all follow me on this? That would be watts per meter. I mean, it's basically watts per meter squared. That's power flowing in a direction. Just with me. Hang on here. So what is this going to be? Power density would be actually equal to, and I'm going to go ahead and put the 1/2 because you have to think 1/2 when you do this the real part, E cross H conjugate, but I'm just going to put it down. It's going to be 1/2 times magnitude, I better do it this way. So amps times volts, this would be instantaneous. This amps over meters times, I'm sorry, density is meter cubed, pardon me. Amps over meter squared times volts per meter. Well, amps per meter squared is J, volts per meter is E. And this is do you remember this class? Now, if you look at this, power density would be per meter cubed. Sorry, I'm sorry about this. Power flow is different than power density. When I take a look at this, the actual power density would be 1/2 the real part of E cross H conjugate. I'm going to just mention that right now. That's what it is. And if you, I'll tell you, I'm not going to go there yet, but what you're going to end up seeing is because of, when we talk about propagating waves, this is going to become 1/2, and because, well, I'll get to this later, E and H, they're related. You can't have one without the other. It's going to be 1/2 times the magnitude of E squared over the magnitude of eta here. It'll be e to the minus 2 alpha z, and it'll be the cosine of the angle of the intrinsic impedance here. It'll be in the AZ direction. I'll tell you what, this is going to be, well, I'm going to come to this later. I just thought about this. I may confuse you if I go right from this derivation to power density, but let me just say this. If you take a look at the actual well, if you would normally say that the current or the amount of power lost would be equal to J dot E is going to be, if you think about that, that would be watts per meter cubed. And that would be the power dissipated. Do you remember this at all? Or not? I'm going to have to go through this and make sure I break this out clearly for everybody in a second. And not, maybe not this lecture, but for sure. Well, since J is sigma E, it's sigma times magnitude of E squared. And this would actually be the power dissipated. And it would be a density, so it'd be watts per meter cubed. Do you all remember that? Do you remember this at all from MMAC 1 or not? You do? Sigma times E squared. This is, the thing is, J is amps per meter, E is volts per meter. Amps times volts is watts. I mean, amps per meter squared, sorry. So this is going to be watts per meter cubed, dissipated. That's the amount of power or thermal heating, you might say, that's occurring in a volume of space. Instead of putting J there, you could just as well put this omega epsilon prime here, because they have the same exact effect. This is a loss term, that's omega epsilon prime, and this sigma is a loss term. Now, I'm going to spend more time getting into this, but this could be replaced by omega epsilon double prime for a dielectric, and you can calculate the thermal heating, the amount of power dissipated per meter cube. I'm going to have to go back and do problems related to this, but I wanted to bring that out. Now, here's something else with this dielectric business. This is sort of an extra to this. This is important right here, what I just did. But when we talk about a lossy dielectric, and in this part, Wentworth doesn't do a whole lot in this book to really expose why this is important. But it is very important when you're selecting materials for dielectrics. You all know what a capacitor is, right? All right, when you look at capacitors, I mean, what fundamentally do they do, in your own words?
Store electrical energy.
Right. They store electrical energy. Typically, they store it over AC cycles, right? Usually, you use a capacitor with something varying AC. Now, you can use them for rectification, right? When you might have a full wave rectifier and you just want to get DC out, you can put a capacitor there, and then you have a slower discharge circuit after that. The capacitor will build to a constant voltage. If it doesn't discharge too quickly before the next full cycle, then you end up getting more or less very little ripple, but you have ripple. To get rid of ripple, they add larger and larger capacitors. Do y'all follow me? Now a capacitor is just going DC here. And we're going to assume this is just going DC, plus or minus VDC plus some V ripple. All right. In other words, you got something like this. Well, this capacitor will always have a plus voltage to a minus voltage. It'll never flip. You all follow me? And what that does is it says the material in here, if it is a dielectric, all the molecules will be oriented in a certain way. The positives will be here, the negatives here. Positives here, negative here. But you get the idea. All the dipoles will be aligned in a certain way. Follow me? Now if you charge that thing and it's just a ripple voltage, these things never flip if it's a small ripple. Does that make sense? Does everybody understand what I'm talking about with ripple? There are electrolytic capacitors. Have you heard that term? Electrolytic capacitors are basically things that always assume you have only one polarity of voltage across. And they're used in full wave rectifier circuits, things like that. Or filter circuits where you have DC and a ripple, but you want to get rid of that ripple, so you put these massive capacitors across where the ripple is. Now, they're gooey, and the dipoles can flip. But when they flip, they heat. And if you have an electrolytic capacitor and you use it with an AC voltage that's flipping, if the voltage is any meaningful amount, any size, that thing will blow up because there's a huge amount of loss. Epsilon double prime is very large for this one. So you'll get basically it'll heat up and blow up. You know how a resistor heats up? All right, that's what's going to happen if it's an electrolytic capacitor. Electrolytic capacitors are used for DC, to get rid of DC ripple, basically. Now, regular capacitors like mica capacitors instead, stuff like that, I mean, because it is a goo, these dipoles will literally flip like this, and that's where you get a lot of thermal heating. It's frictional heating. But in a mica capacitor, in every other kind of capacitor that has a solid dielectric, those dipoles never move. Y'all follow me? They'll stretch, but they can't spin. They can't reorient. That's the problem. Well, that isn't a problem. That's the nice thing. However, those type of dielectrics have a much lower breakdown threshold, typically, than electrolytics. Electrolytics can have a huge voltage, which makes them nice, and they have a large epsilon relative, so they store a lot of energy. Do y'all follow me on this, class? You can look up electrolytic capacitors. You should be familiar with this because some of you will be working around probably pulse power applications and stuff, and you have to know you can't just use an electrolytic capacitor for anything where you could get reverse current through. I've been around a railgun, this is years ago, and when we were building it, they showed us some stuff. So they have these high energy density capacitors storing an enormous amount of energy, DC in it. And they showed me the aftermath of one where reverse current got into it. Basically, they're discharging something, huge currents, 20, 30 kiloamps currents, but instead of just having it went through it in the wrong direction, basically, and changed the polarity, and the whole thing blew up, and they showed me it was like a grenade went off. The whole front end of the capacitor is blown out. These are 250-pound capacitors, and all that metal and goo went blown up in the complete. I wasn't told anybody was hurt, but I can imagine if you were nearby, it's like a grenade, honestly, when it went off. So that's the thing. With typical capacitors, mica and stuff like this, they don't. And they have very low let's say, low values of epsilon double prime. So in order to get a figure of merit of how good or bad a capacitor is in terms of loss, what they do is something they call it the loss tangent. Loss tangent. And can you take a look at the page number on that one? I should have brought my book down here. This will be in his when he talks about lossy dielectrics. He's just going to have loss tangent. I'll show you what he does.
What page is lost tangents on?
Well, yeah.
333 or 333.
Page 333 in Whitmer's book. Now here's what they do typically. They're going to plot And they'll pull out the real part of what they're going to do down here is have epsilon double prime. Let me put it this way. This is a real part where it's like the sigma e term. They'll have omega epsilon double prime times e here on this axis. And on this axis, they're going to have omega epsilon prime times e. Now, if you look at this, what it really is a plot of epsilon double prime, or epsilon prime, over epsilon double prime. I'm going to go ahead and just do it this way. I'll just say this is a plot of epsilon double prime, this is epsilon prime, and here's epsilon complex, which is epsilon prime minus, and j epsilon double prime. I should actually have this as the minus j axis. Do you see this in Wentworth's book?
See something like it.
He's got it. That's it. Go down. You see how he has, okay, he puts sigma there, but this is omega epsilon double prime on the bottom and omega epsilon prime on the top, but he does multiply by the E field, and he puts sigma in there. Get rid of sigma. This is on page,
This is 333.
and it's figure 8.2, right? Or is that, I'm sorry, 6.2, 6.3. Figure 6.3. Now he includes, he does this, he puts sigma plus omega epsilon double prime times E, and then over here he puts omega epsilon double prime times E. Well, what he's really plotting, and he should be plotting, is epsilon double prime versus epsilon prime. What we really care about is this, okay? What he's doing gives us the same results. And here's the thing, if you take a look at this, we're really interested in this value. I mean, really the tangent of this value. Now, if you think about this, from here to here, that's epsilon double prime. From here to here, that's epsilon prime. And this angle right here, just write this down. This is going to be, or the tangent of that angle, is really equal to epsilon double prime over epsilon prime. Can you all see that? I want you to make sure you see this, and I don't want to confuse you. I'm sorry about earlier. I was going to go somewhere with that, and then the more I thought about it, the more I thought I'd better not do it right here because I need to cover a few more steps. Follow me on this one. Remember, epsilon complex is epsilon double prime minus j epsilon double prime. I'm putting the minus j axis there to keep it consistent with what he shows. You with me, class? Don't worry about the real and imaginary part of the current, all right? Right now, just look at epsilon prime and epsilon double prime. Here's the actual epsilon complex. The loss tangent is really this angle. And what it is the ratio of epsilon double prime over epsilon prime. He has that if you look, right?
Yeah.
What equation is that? This is
Tangent.
called loss tangent.
Equals sigma plus omega,
Sigma 0 for this going on.
omega,
6.55.
All right, take a look at equation 6.55. Is that the one?
yeah, that's the same one. Yeah.
The sigma you ignore. It makes no sense to talk about loss tangent if you got sigma. It just doesn't. Now, if you take a look at this, loss tan here will be very small. It'll be like 10 to the minus 4th, 10 to the minus 5th, 10 to the minus 6th. But here's the deal. The loss, the tangent of an angle that's small, if it's in radians, is about the same thing as the angle if it's in radians. Do you all agree with that? So if you look in the back of your book, he's going to have a table, and he's going to show you the loss tan for a lot of different dielectrics. Does anybody have the actual book? You've got the book. You can find it right within a minute. Make sure. I'm just showing you what you need to know on this one. My book is falling apart. I don't even know that, so I have to do it for desktop users. This is no than mine. find it before me. Here we go. This is on page 625. It's table E2. And he's going to have tangent of delta, and that's the loss tangent for a whole bunch of materials. If you take a look at that. See it? He's just exposing you to this. Are you familiar with this or not? I'm just asking because I'm trying to figure out how I should wrap this up. Have you heard of loss tangent or anything? It's just a figure of merit of how good it is. Now the thing about it is, you're going to see he has air, and the loss tangent is 0, right? First one, right? Then he's going to have now take a look. He keeps going down there. What's the one with a large loss tangent, like 10 to the minus 3, 10 to the minus 4? And it is frequency dependent. You see it? Which one? Polystyrene, or which one is it?
Gold, oh wait, I'm sorry.
No, not metals. E2, table E2.
Mica, or mica.
What is mica?
10 to the negative, 3 to the negative, 3 times 10 to the negative 4.
All right, that's not really lost. Now when you get,
Seawater is 0.9.
yeah, seawater's horrible. But but what else? Seawater is what? And that's at a given frequency, right?
That's at 1 megahertz.
All right. Seawater is something that's gooey. It basically flips, right? So it could be used theoretically, even though it's a horrible material. It could be used as a dielectric to get rid of ripple. But the thing is, it can't be used for anything but an electrolytic kind of capacity. Because if you use it for AC, you just blow up. I mean, it would heat up like crazy. That's how your microwave basically works. It heats things that have dipoles that flip it. I mean, I'm sure everybody's familiar with the microwave oven. That's what happens with these things. So that just gives you an idea. So in the problems he has trivial problems. You know, calculate the value of epsilon double prime for like air at 1 megahertz or something with 0. Follow me on this? But you have to be at least aware of this. Okay. Now we've got that. Now, the next topic of interest, if you take a look, we've gone through conductors, we talked about the velocity, we talked about all that stuff, we talked about dielectrics. You just want to see in his book, I'm very sorry to go down, propagate, we're done with dielectrics, you can just keep going down, scroll down. Yeah, we talked about propagation and the attenuation. Go ahead. All right, we talked about skin depth, right?
Yes.
Did you just add it, or? Okay, that's all right, but keep up with it because you're getting a quiz Friday. All right, so make, go there. Power propagation. I'm going to go ahead and do power, and then I'm going to do the important part today, and that's going to be reflections. And this is going to be important. I'm going to formally do power. This is power flow, not power dissipation, and I'll make it clear. That's where I was going with this, but I went a little too far ahead, unfortunately. All right. So if you have an electromagnetic field propagating, this is the E field, and it's propagating in this direction, say it's the Z direction, call this the X orientation in this direction. So the wave's propagating in that direction. It has to have an H field associated with it, right? Remember, E cross H has to be the direction of propagation. Is everybody with me on this? So I told you that E cross H was the pointing vector, and the pointing vector gives you the power flow. There's an instantaneous form that I'm going to write down. Instantaneous form, and that is simply, now I call it S of T. This is the most common symbol for pointing vector. This is the pointing vector. But he will use P of T. And I believe he has P of T, and he may have P average of T, which is kind of misleading. But what they are is this. It's going to be simply E of T, and that's a vector crossed into H of T. Now, if you look at that, that is an instantaneous value. It's time domain. It means it varies with time. You remember when you had power in like your circuit course, right? Average power flow for a constant sinusoidal waveform is much different than the instantaneous value. Instantaneous can be positive, right? And then it goes to zero. Then it has a big peak, goes to zero. Big peak goes to zero. Do y'all remember that? Well, that's the instantaneous value. Same with the instantaneous value here. We don't really care about that most of the time. The units would be watts per, and if you think about this, volts per meter, amps per watts per meter squared. And it is the power flowing through a certain area. But what we really care about is the average power density, and really P-av, and it's a function of Z, by the way. And that's given, and he has it there as 1/2 the real part of E crossed into H conjugate. I'm going to do this for you. I showed the answer to this one already, but I'm going to do it. Now, this is for propagating waves. I want to make sure I say this. Everything that we're talking about in this chapter has to do with propagating waves, not DC effects, and not waves that are not propagating, or not electric or magnetic fields not propagating. As a quick kind of review, I wanted to, I don't think I mentioned this in this class. If you had something where you have a capacitor charge plus to minus a voltage is the capacitor, right? If you looked, you could see electrostatic field mapping, if we could somehow envision it around it. Do you all follow me on that? That electromagnetic field can vary with time if I put a time-varying voltage on, but it's not propagating. Nothing is launched. If I just have a capacitor and I charge it to a voltage, there's an electric field out there, but no energy is being lost. All the energy I put into that capacitor I can get out. Do you all follow me on this? The stored energy is 1/2 CV squared. If I go ahead and I shorted a resistor across that, all that energy would be dissipated in that resistor as heat. With me? Typically it's heat. Now, if you have an inductor and it has current flow in it, then you have a magnetic field. The magnetic field is all around, theoretically. It's concentrated near the coils, but it is not propagating. And all the energy in the magnetic field can be gotten out. The magnetic energy the inductor has is 1/2 Li squared. All the energy in a capacitor or an inductor you can get back. But if you have an accelerated charge or time-varying current, which is charge accelerated, then you launch waveforms. You launch energy and power, theoretically, into space, and that can't be gotten back. You with me, class? Those are propagating photons. Anytime you talk about electromagnetic energy in either a capacitor or an inductor that you can pull back, that's called virtual photons. And this is well beyond the scope of this class. Have you had virtual photons at all? Have you had quantum? You had quantum, right? Did you have photons? Well, photons, real photons have what? Mass? They don't have mass, but they have momentum.
Yeah.
Virtual photons don't have either. But virtual photons have energy. And that's because they're static, they don't move. And this is complicated stuff. As far as, this is not my area of expertise, but I have to know this because some of the stuff we deal with. Now, when we're talking about launching propagating waves from antennas and stuff, that power never comes back. It's launched forever. That's what we're talking about here. So this is the average power density, and the units would be watts per meter squared. It's how much power is going through the surface of a per meter squared. Like the sun's radiation that you feel is it's actually a propagating wave. It's actually an ensemble of a whole bunch of different frequencies and photons that you can feel, but it's propagating, and so you can feel the heat hit you. I come down here, and if it's a propagating wave, and we talk about E and H, well, I know if I have an E field, I have an H field, right? And the H field for a propagating wave would be actually equal to E naught, if you think about it, over the magnitude of eta. Now, I could do what? To get H, I could go through for the phasor form. I could say it's equal to 1 over eta, unit vector in the direction of propagation crossed into E. Y'all with me on this class? We could do that. I'm writing down what it is, but I'm going to take, I'm going to say that eta has a magnitude of eta. This is the intrinsic impedance, and it's at an angle, E of angle of eta. And you know that eta, the intrinsic impedance, is square root of j omega mu over sigma plus j omega epsilon. Is everybody familiar with that? Do you remember? I want to make sure. Do you remember? I know. You don't remember? Were you in the last class? Were you in the last class? Do you remember? You don't remember intrinsic impedance? That's what this is. It's called the intrinsic impedance. That's what that eta symbol is. Now, so it has a magnitude. This, in general, is complex. It would have a magnitude and it has an angle. To get this h, normally it's 1 over eta. Well, eta here, I might as well do this. I'm going to do it the way consistent with Wimmer's book. Wimmer's going to talk about this, but we're going to do something, and I'll get to that first. First, he assumes that the E field here, the actual phasor form of the E field, has a magnitude E naught. It's e to the minus alpha z. Now, alpha could be 0. Then it's going to be e. I better do it this way. The E field itself is going to be equal to some E naught, e to the minus alpha z, e to the minus j beta z in the AX direction. We're assuming that the wave is propagating in the z direction, but it's oriented in the x. Y'all follow me in this class? This is consistent with what he has. Y'all with me on this? Do you remember this? Now from that, if I want the direction of propagation, what is it for this one? Just by looking. I decided already. Class?
AZ.
It's a unit vector in direction of propagation is positive AZ, right? You determine that just by looking at this. Because the z tells you that e to the minus j beta z, it's going in the z. The minus j tells you it's going in the plus z. So it's AZ. Now, if we look at this, and now we want h, you'll need to know these, the simple tricks to get e from h and h from e. Do you remember those two? Y'all did the problems, right? Remember? That was one, and what's the other? E is, class?
Negative
Minus eta, right? Unit vector of direction of propagation crossed into h, right? So if you have h, you can get e h if it's a propagating wave. Remember that eta there has a magnitude and angle. That's the key. So when I get h from this equation, I'm going to say h is equal to 1 over magnitude of eta e to the j, and I'll just call this theta eta, which is the angle associated with the impedance. Unit vector in the direction of propagation. We're assuming it's an AZ, right? And then it's crossed into the E field. Well, the E field is right here, and it's equal to E naught e to the minus alpha z e to the minus j beta z in the AX direction. Does everybody follow this? I'm just putting in, by definition, I'm replacing things, right? Please watch. You'll need to know how to do this clearly so you don't get confused with this. All right, maybe I need to blow this up a little.
And this is because sigma's 0, right? Are we still assuming?
No, sigma's not 0. This is a general form. Sigma, matter of fact, we can assume, we're assuming this could be complex, so sigma is not 0. And so gamma is equal to alpha plus j beta is equal to the square root of j omega mu times sigma plus J omega epsilon. You all with me? You have to make sure you know these things very well. I mean, we use them all the time. So getting back to this thing, I can take a look at this and I can see I have E naught and I have eta, so I can take E naught over the magnitude of eta. And then I have AZ, or then I can put e to the minus alpha z here. And I can go ahead and write e to the minus j beta z. So I'm just repeating all the terms that have no real vector sense to them, or angle. Now when I take a look at this one, I have e to the 1 over e to the j theta of a. When I take it upstairs, it becomes e to the minus j theta associated with the intrinsic impedance. Because if it's plus downstairs, it becomes minus upstairs. Everybody okay with that? Finally, I'll have AZ crossed AX, which is
AY.
AY. And this would be watts per meter, amps per meter. Everybody agree with me there? Okay. I'm trying to go through this in a way that won't confuse you. I'm doing more theory. I want to be clear about the theory because it gets real important in a second. So now we're getting back to this average power. This is the key thing. You take the average power here. It's 1/2 the real part. Now E, I'm just going to rewrite E. E naught e to the minus alpha z, e to the minus j beta z. All right, that's just rewriting that in the AX direction. And it's crossed into the H field. That's the H field, and it's E naught over magnitude of eta, but it's the H field conjugated. And I forgot to put that conjugation symbol, I'm so sorry. Let me mention something about that conjugation. Remember how average power flow, or power in a circuit, average power, was 1/2 the real part of V times I conjugated? You all remember that? So conjugation occurs here as well. And it's H conjugate right here. I'm sorry I didn't put it more clear. So when you do that, and you conjugate the H field, what happens is this real part, e to the minus alpha z, stays the same. But when you conjugate it, you've changed the signs of these. Does everybody know what conjugation is? Are you familiar with the term conjugation? When I say something is conjugated, if I say A is 5 at an angle of 40 degrees, what is A conjugated? Class? The symbol for conjugation is an asterisk.
Negative 40 degrees, 5 and negative
5 at an angle of minus 40 degrees. Do you agree? That's what conjugation does. It changes the sign on the sign of the angle associated with the number, polar number, or exponential, right? So here, when I conjugate, I'm going to go ahead and change the sign on that J beta in the phase angle. So when I do it, I get what? E to the plus J beta z, right? And then it's e to the plus J beta n. And I need the real part of that. Can y'all follow me? I'm just throwing it all together and making sure I didn't drop anything.
So is your average power like a per meter unit then? Since you
Meter squared.
Okay.
Power density.
Oh,
It's a density. And you can almost tell by the units, right? You got electric field, volts per meter, H, amps per meter, volt amp, watts per meter squared. All right, now take a look at this just for a second. It's the real part. That means I pull out E naught, I pull out magnitude of eta. I have e to the minus alpha z twice, so it's e to the minus 2 alpha z. So the rate of decay of power is twice as fast as either the E field or H field makes sense in terms of it's 2 alpha z. Then I have e to the minus j beta z times e to the plus j beta z, which is e to the 0, which is 1. So that goes away. And then I have ax crossed into, and I didn't put it here, ay, I should have, which is a z, right? Az. And finally, the last thing that people forget, you'll notice it's the real part. We've taken care of everything but this e to the j theta eta. What's the real part of e to the j theta eta?
Cosine.
That's right, just the cosine angle there. So it's cosine of that angle. And that is the average power flow in watts per meter squared. And he has that in his book, but that's how you get it. You've got to remember one thing, and this is important too. There's no beta in that term. You all see this? Beta's gone. It's not, well, it's at an e to the j minus j beta. That's gone. It is decaying as e to the minus 2 alpha z, and you do have to take the cosine there. Now, that value, that angle of the intrinsic impedance, the largest value you can have is 45 degrees. And if it's lossless, the angle is 0. What's the cosine of 0? 1. Cosine of 45, 1 over square root of 2. So the most reduction due to that cosine term is just 1 over square root of 2, about 70%. So just keep that in mind. So that's average power flow that he shows, right? Now the next, I know he shows it there, but the next thing is going to be reflection. I just want to make sure that he doesn't jump and do something else.
Polarization.
We'll do polarization later. Polarization is something trivial, but that he's going to have reflection coming up. Keep going. Keep going, keep going. Keep going, don't worry about that. Yeah, there we go, reflection and transmission, section 6.7. Now this is important, and I want you to please be attentive here. I'm not going to go real fast, but I want to make sure I don't lose anybody. This is the stuff that becomes really important, especially when you have oblique angles. For instance, so here's the statement of the problem. This is all propagating electric fields. We're going to have a barrier, and this is going to be air. Doesn't have to be air. And air has eta naught, which is 120 pi ohms. We're going to have a barrier here. This is the z direction. We're going to say the difference in media occurs at z equals 0. This is the z direction. We call this the x direction. Can y'all follow me? Now this material here is going to be material 2. There's going to be a different material. As a matter of fact, I'll call this region 1. So in region 1, the intrinsic impedance is eta naught. And region 2, it could have a value of sigma, it could have an epsilon, it can have a mu that aren't equal to free space values. Y'all with me? Now, that means that this region will have a different intrinsic impedance. So this is media 2, and the intrinsic impedance of this media will be equal to the square root of j omega mu over sigma plus j omega epsilon. Y'all with me? That's a definition of the intrinsic impedance. And we're going to do this in the phase line. We don't know what it is, but it's going to have a magnitude and that. It's going to have some magnitude of eta 2 And it's e to the j, and it would be angle of eta 2. We don't know what it is. Now, we're going to assume we have a propagating wave over here. And it's an incident wave, so it's going to have an electric field incident. It will be in the x direction, and it's propagating into this boundary, and it's going to hit it. Then, some of that waveform is going to be transmitted, some of that wave. So there's going to be an electric field that's transmitted, and it's going to keep flowing in the region 2. But there's going to be an electric field that's reflected. And let me do it down this way. So I'm going to have an electric field that's reflected here, and that one's propagating in this direction. And I'm going to have an incident, a transmitted, and a reflected field. With me on this, class? And I'm going to write the definition, or I'm going to write the mathematical expression for this. So the incident electric field will be rendered as, keep it consistent with Dr. Wimperspoon. E naught, I'm putting it in air, so it's going to be E naught minus J beta 1 times Z here. And it will be in the AX direction. And this is going to be E naught incident. Then I'm going to say E reflected, the reflected waveform, is some E naught reflected times E. Now it's going in the opposite direction. A reflected wave is going in the plus Z direction. I mean negative Z direction, right? So this is going to be E naught reflected, but it'll be plus J beta 1Z in the AX direction. Same polarization, only this one's moving in the minus Z direction. Can you all follow me in this, class? Then you're also going to have a transmitted electric field. And the transmitted electric field is going to be E naught transmitted, and it's going to be times E, and this could be minus alpha, and this would be alpha 2Z times E to the minus J beta 2Z, because it could have an alpha term, and it probably does, and the AX direction. So we have three components to the E field: the incident, reflected, and transmitted E field, as they're mathematically given. With me? Now you're going to have three components to the H field. You're going to have an H incident, and I'm just going to tell you what it is because I told you the right-hand rule, right? E cross H, direction of propagation. We see the E field's in the X direction. It's propagating in Z. Therefore, this is going to be equal to some E naught incident over eta, right here, or eta naught, if you will, because I'm saying this is free space. E to the minus J beta 1Z, it would be in the AY direction. You all follow me on the reasoning behind that? Remember how I got that? I would take, normally that's 1 over eta, unit vector in the direction of propagation crossing the E field. The E field over there is stated, so that would be the reflected H, or I'm sorry, the incident H field. How many know that? How many see that? Do you see it or not? No. I mean, have you did the problems? All right, do you remember how to get this from, I erased them, but those things, well, this is just the definition of the H field. You can always get it with the right-hand rule. E field's in the X direction, it's propagating in the Z, H has to be Y. Now, if you look at the reflected electric field, H field, think about this. Electric field's vertical, it's propagating that way, right? So if that's X, Y's out of the board, isn't it? X cross Y, Z, right? Right-hand coordinate system. You all know what I'm talking about here? Well, if it's propagating that way, which way is H? E crossed H would be in the minus Y direction. You all see that? And you can get it with the other rules. So it's going to be minus E naught reflected over eta naught, E to the plus J beta 1 Z A Y. Finally, what is the transmitted H field going to be? Well, I'll give you a tip. It's going to have the same exact orientation. I mean, the H field that's transmitted, same orientation as the H field that's incident. Because the E field is in the same direction and propagating in the same direction. You all with me? So it's going to be plus Y. And this is gonna be E naught transmitted over, now this is eta 2, right? And might as well put that, no, I can just leave it as eta 2, it's all right in this case. And then it's gonna be E, I better do this, E to the minus alpha 2z, E to the minus j beta 2z, and here it's gonna be E 2 times z, and it's E to the minus j angle associated with eta 2, and it would be in the AY direction. Now I've got all these terms down, and the reason I put them down, I'm trying to make you think about this the way Wentworth's book, the way he did these proofs. Each of these E fields has an H field necessarily associated. Now at the boundary, and this is where we use boundary conditions. These are called boundary conditions. Remember from EMAG 1, tangent electric field, E tan 1 is E tan 2. And if there is no surface current, H tan 1 is H tan 2. Do you all remember that, class? So based on that, I can say E tan 1 equals E tan 2. These are tangent electric fields, and I'm going to make a point. When I talk about tangent, like if I have, I'm just going to talk about this whiteboard right here. If I say an electric field is oriented this way, it's propagating in the whiteboard, you see how the entire electric field is projected in the plane of that board? That is tangent to it. If it was normal, if I said I had a vector like this, and it was somehow moving in this direction, then that vector would be perpendicular to the plane of the board. That would be normal. All right, not tangent or perpendicular. You with me on this, class? So over here, E tan 1 equals E tan 2 means the tangent fields on either side of that boundary at z equals 0 have to be the same. Do you see that in your book, by the way? Or in your notes? It is. So here, E tan 1 is E tan 2. What is the tangent field on this side in here, region 1? Well, it would be at z equals 0. Do you all follow me? You always make sure you put z equals 0. You ask for a lot more math than you need. Well, z equals 0, this e to the minus j beta term has no bearing. So tangent on the first side would be E naught incident over eta 1. The reflected field, remember the reflected field right here, right here, is going to be plus E naught reflected over eta, I'm sorry, I don't have eta 1, I'm sorry about that. It's just E naught incident plus E naught reflected equals E naught transmitted. You follow me on that? That's tangent on one side, is tangent on the other. The tangent fields will occur at z equals 0. That's the boundary. This is where the separation occurs. Now, the next is H tan 1 is equal to H tan in region 2, correct? These are the tangent fields. I mean, the tangent fields would be at z equals 0. The incident reflected would be on one side and the transmitted would be the other. You've got to take note of that negative sign. So over here, H tan 1 is H tan 2 means E naught over eta naught or eta 1, either one. As a matter of fact, I can do, I'll put it as eta 1 because that way it'll open it up. Anything minus, this is E naught incident, minus E naught reflected over eta 1 is equal to E naught transmitted over eta 2. Can you all see this, class? Again, it's at z equals 0. I'm taking the H field that's on one side. At z equals 0, all the exponential terms go away, right? And I'm equating them to the E field on the H field on the other side. Now I have two equations right? Right here is 1, here's the second. Now I'm going to get a ratio of the incident to the reflected field and the ratio of reflected to the incident field and a ratio of the transmitted to the incident field. So if you take a look at this for a second, I think you can figure it out. I've got, I have E naught minus E naught incident minus E naught reflected over eta 1, and I have E naught incident over E naught reflected here. Correct, class? You all see it? I want to get one equation with one unknown. So the thing I'm going to do is just rewrite this. So I have E naught incident right here minus E naught reflected over eta 1 is equal to E naught transmitted over eta 2. And I just restated what I have there. And now I use the first equation. And I go ahead and I'm going to say E naught transmitted right here is equal to E naught incident plus E naught reflected. So I have E naught incident minus E naught reflected over eta 1 is equal to E naught incident plus E naught reflected over eta 2. Y'all follow me on this? Now you manipulate. Now what I'm going to do next, let me just tell you this because I know you're writing. And it's easier to do it this way. I'll divide everything by E naught incident, and then I'll define some terminology. I'm going to define E naught reflected over E naught incident as the reflection coefficient. This is the reflection coefficient. Right here. So I'm dividing everything by E naught incident. I get 1 minus the reflection coefficient over eta 1 is equal to 1 plus the reflection coefficient over eta 2. Can you all see this? And now we solve for the reflection coefficient. Multiply both sides by eta 2, eta 1, and then gather the common term gamma, or the reflection coefficient on one side. And what do you see happening? I know I'm about out of time. There's a reason it's this way. So you see it's eta 2 minus eta 1 over eta 2 plus eta 1. And this is the definition of the reflection coefficient. Also, the transmission coefficient is E naught transmitted over E naught incident. And here, that one can be proved to be 1 plus the reflection coefficient at the boundary. And it's also equal to 2 times eta 2 over eta 2 plus eta 1. Do you remember this from transmission lines? Remember with transmission lines, we didn't have eta, we didn't have characteristic impedance, we had actual impedance as Z, right? And the reflection coefficient with transmission lines is the impedance you're going into minus the impedance you came from over the sum of the two. Here, it's the same exact formulation, only these are intrinsic impedances, not actual impedance values. So here, it's eta 2 minus eta 1 over eta 2 plus eta 1. And the transmission is just 1 plus reflection coefficient for normal incidence. Now, gotta say one thing about these. I know you've been with me a long time. I did a lot of talking today, so just listen. When I look at this reflection coefficient here, what happens, what is the reflection coefficient if we say we have eta 1 is 120 pi and eta 2 is 0, a very good conductor. What's the reflection coefficient? Just look. That would be a short circuit basically. Suppose you have copper plate conductivity is so high, eta is going to be about 0. Trust me on that. The intrinsic impedance, and you're coming from 120 pi. So what's the reflection coefficient going to be? Well, eta 2 is 0, right? 0 minus eta 1 over 0 plus eta 1 is minus 1. So, very good conductivity, you get minus 1. Now suppose the opposite, well, you can't actually do the opposite, but the thing is, the other extreme possibility, and it will never get to this value. What if eta 2 gets very large? Just listen to me. I mean, instead of 120 pi, say it's 120,000 pi, which is, you take something, refine a material like that. Well, then it's really eta 2 minus 0 over eta 2 plus 0, or it's 1. With me? So the extremes for reflection coefficient are from 1 to minus 1. And what happens if eta 2 equals eta 1? 0. Nothing is reflected. That's something where you have no discontinuity of impedance. It's a perfect match. Do you all follow me? It's like a transmission line. When your load Z0 is Z0 and your transmission line is Z0. Now, for transmission coefficient, it's the easiest way for normalists is just take 1 plus reflection coefficient. So, just look at this for 1 second. Here, if eta 2 is 0, reflection coefficient is minus 1. That's like copper. What's the transmission coefficient? 0. That makes sense. Nothing would be transmitted. With copper, almost everything's reflected. That's the reason I use that example. And I'm just mentioning these things because some of this stuff, until you actually do problems with it, seems abstract. So for your quiz on Friday, I'm going to base it on the last couple of homeworks, but I want you to make sure you do the homework for reflection and transmission coefficient, okay? The stuff I'm about to put up. And we'll go over some of this stuff. I think that'd be fair. Okay. And the quizzes are based on the homework. I'm really tired. I worked out and I haven't eaten at all, so I'll make sure my stuff.
Yeah, you should get help. All right.